Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome back to this series of lecture on solar energy conversion, and today here we are at the last lecture, which is lecture number 35. Okay. So, today we are going to talk about the real interesting thing, which is when light falls on the photovoltaic material or the PN junction diode, what happens? Okay, what magic happens that it gives you electric current. Okay. So, up to the last class we have looked at the dark IV equation, which is given by right, and here this is the reverse saturation current, right. This V is the applied bias or voltage, okay, and this is the current. So, you can see this equation is valid when there is no generation, that means no illumination by light is happening, and that means there is no generation of electron hole pair. Now, when you illuminate, diode is illuminated, right, with solar radiation. It can be other radiation as well, but to create the radiation you will require energy. So, that does not make sense. The radiation which is already available through sun, that is what we are going to use for conversion into electricity. Okay. So, when that happens, we have generation of electron hole pairs. So, this generation term G, we have introduced it in the continuity equation, but every time before using that continuity equation we set it to 0, right, because there was no generation happening. And so, of course, whenever there is generation, there will be some recombination as well, recombination of a fraction of that. Okay, or I should not say fraction of that, it is basically recombination of all of that if you take out the generation, and after a certain time everything will recombine, because there is no extra energy to sustain that generation. Okay. Recombination of EHP, which is also called annihilation, because recombination means the electron and hole, both the carriers are now gone, annihilated. So, recombination of HP after a certain lifetime, or you can equivalently call it, quantify it by a recombination length. What does recombination length means? After travelling this much distance, the average electron hole pair will recombine. That is what the recombination length means. We have introduced this earlier. The Ln and Lp, those are the recombination length of electron and hole you have seen. So, average length travelling which EHP recombines. That is the meaning of recombination length. Okay. Now, whenever we have illumination, so this generation will happen everywhere equally, right? Generation everywhere, what do we mean by that? We mean that the p side quasi neutral region, okay, space charge region and n side quasi neutral region. Everywhere this thing will happen. Okay. Everywhere the EHP numbers will increase by equal amount, because we are assuming the illumination is same everywhere. So, the generation will happen in equal amount, but you think of this. Okay, let me draw it with figure so that you can visualize it easily. So, this is our standard figure we have used multiple times. This is our SCR, space charge region, and this is our p side Qn quasi neutral region QNR, and this is n side QNR, right. So, when light falls everywhere the generation is happening, but for the quasi neutral region there is no field to guide those added carriers, right. So, for quasi neutral regions no field, right, to guide the added carriers through generation, right. So, what will happen? You think of it physically, you close your eyes and think of it that these things will generate, and then each of them will get recombined after travelling a certain distance or after a certain time period tau n tau p. Okay. So, and the generation will happen at the same rate, recombination will happen at the same rate. So, effectively you will have an extra amount of or extra concentration of electrons and holes, but they are ineffective, they are not contributing to the overall current, because if you do not have a concentration gradient there will be no diffusion current. Just adding the concentration will not give you any current, right. So, if that is the case, then recombination and generation happen at the same rate and they effectively contribute nothing to the current, right. So, where the interesting thing happens? It is in the near the space charge region. I am not saying only in the space charge region, but near the space charge region. What do you mean by that? So, SCR where you have xi not equal to 0. So, you have a guiding force or a field to guide this extra electrons and holes in proper direction. Okay? And what is that called? That is called drift current, a current that is generated by the guidance of a field. So, there will be drift current. Okay. And not only in the space charge region the carriers will be guided, but the near the space charge region, some region in the quasi neutral region, let me just draw it again. If this is your space charge region, and let us say in each side there will be a certain neighboring area in the quasi neutral region. So, this part is neighboring length near the space charge region in p side. Okay. Here this is the same thing, neighboring length near SCR in n side. Okay. Now, you think of these closed areas nearby the space charge region. Here the generated electrons and holes, they will move around randomly, right, and the length after which they recombine is known, that is called recombination length, Ln or Lp, right. Now, if you have some particular electron which is up to that length from the space charge region, it has a probability of drifting near the space charge region or at the edge of the space charge region. If it reaches that edge, then it will be sucked into the other side, is not it. So, in that case we can say that this length is the recombination length for minority carrier in the p side, which is recombination length for the electrons. Okay. So, this is recombination length for the minority electrons in the p side which can reach the edge of the space charge region to be sucked into the other side. Right, and similarly you can say this is the Lp, which is the recombination length for the holes in the n side, and you see that only the minority carriers which are playing a role here, because this is all drift, there is no diffusion current, it is all drift due to the field, and it is only near the space charge region. So, let me just summarize these observations. So, the interesting stuff is happening only near the space charge region, right, and the current is only due to drift, because xi is non-zero near or at SCR, right, at SCR, but the effect is felt nearby region as well, because the added electrons or holes, they can come drift near the space charge region edge just by thermal agitation or thermal movement, and they can be sucked into the other side. So, and okay, here the major observation is the minority carriers are playing a role, okay, not the majority carrier. So, you see that majority carriers, they are giving you the background diffusion current and all, okay, and they are of course important. Without getting the majority carrier, there is no point having minority carrier, okay, they are interlinked, okay. But in the photovoltaic effect, whatever you are getting, the interesting stuff is all contributed by the minority carriers. So, it is very important and I would say very subtle point which you should keep in mind. So, the net effect, what you will find, so if we try to find what would be the light generated current, that means when you illuminate, what would be the effect in terms of current. So, this light causes large drift current, just as we have seen right now, drift current due to minority carriers, okay. And very important, very subtle also, drift current is always in the opposite direction of the bias, right. So, it is from N side to P side, right. So, opposite direction of the forward bias. So, forward bias direction is what? It is from P side to N side. P side is positive, N side is negative, okay. But for the drift current, the current is in the opposite direction, right. You have seen it couple of classes ago that why drift current is in the other direction, okay, because the drifting happens only downhill of energy for the carriers. So, this opposite direction you have this drift current. So, the net effect is a negative shift in the current axis in the IV characteristic curve. Okay. So, for any value of bias, any value of V, you will have that offset, a constant shift in the negative direction of current. Okay. That is the physical reason why we are getting it. So, earlier what did we have? We have this particular VI characteristic curve, right. So, this is the positive V and this is the positive I direction. Okay. Now, due to light, what will happen? This whole thing will be shifted downwards for any bias. Okay. So, you see that everywhere it is shifted downward and they will be parallel to each other. Okay. So, what should I say? That these two lines are parallel to each other. Why? Because the light generated current, it will, and how much shifted, that will depend on the degree of generation. If the intensity of light is higher, you have more energy to make more electron hole pairs, right. So, the shifting will be larger, and for less intensity you will have less shift. So, these are very important points. So, the degree of generation, which will of course depend on the intensity of light, okay, will determine the shift from the dark IV curve to the illuminated IV curve. Okay. So, this one is our dark IV curve and this one is the illuminated IV curve, isn't it? Are you getting the concept? It is important you think through this again, if the concept is not clear, but from the start of this class up to now about 20 minutes, you please go through again and try to visualize why this parallel shifting towards the negative current direction will happen. Okay. And this particular shift, which you can call let us say here only, let us show, because that is on the current axis, we call it IL. Okay. So, this IL is called light generated current, and note that it is in the negative direction. So, current is positive when it is flowing according to the forward bias direction. Okay. Here it is happening in the opposite direction, that is why we are calling negative direction. Now, if you look at this curve little more closely, then you can see that in the fourth quadrant of the illuminated IV curve, we have positive voltage, right, and negative current, right. So, Vi, if you multiply, what will happen? You have a negative value for power. That means power is getting generated, not consumed. If the power was positive, then the Vi is positive, that means power is getting utilized in the process, right. But here with a negative sign, Vi gives you power that is generated. So, power which is Vi, it has a negative sign. What does that mean? That power is getting generated and not consumed. Okay? And that is what we want. We do not want our PV cell to consume power. When you apply some voltage and then illuminate light on it, you will have some current output in the circuit, that means power is getting generated. So, now if we want to quantify this, quantify the light generated current, so we have to take into account what is the contribution of the space charge region and the nearby regions Ln and Lp in the p and n side respectively. Okay. So, the total contribution to the extra electron hole pairs generated, pairs generated due to illumination okay, total contribution to the drift current. So, the whole generation happening in the area Ln plus W plus Lp, this is the whole area that is getting used for generation of drift current. Okay. And if we have, so this is the area, so total current would be this IL rather would be your Q into area, area is the area of cross section we are saying, and then rate of generation multiplied by this length or this effective length for which the p-n junction diode is contributing to the drift current. So, you can see that this is the rate of generation and this area is our cross sectional area okay, in the opposite direction, and this is the charge. Right. So, this will be the total amount of drift current that you get. So, ultimately what you have I, which is the total current, it will have the earlier we have the dark IV equation. So, from there we will have right, this we have seen in case of IV curve for dark situation, and then we have this minus shift which is isn't it. So, I again draw your attention to this negative sign. So, in concise form what we can write, I equal to I naught e to the power q v by k t minus 1 minus I L. Okay. So, this is what we get after all these different kinds of, I mean, going through the band structure, how the Fermi level is changed, how doping contributes, now under equilibrium how the currents are distributed, okay. And then we introduced a bias to break that equilibrium and see under the dark situation what would be the current. And for and after that we introduce the light, the effect of light on it, and we have gotten this final equation which is called the photovoltaic IV curve. Now, we have light also. So, it is different from the dark IV curve, and here, so this IL I naught is we have already mentioned. IL is the added part which is causing everything interesting. So, now if we look at a solar cell, so a solar cell is expected to produce power, right, and that means I and V are in opposite direction, as we have seen earlier that in the fourth quadrant which are actually giving us meaningful operation, but that often confuses us. So, what we do to avoid this directional confusion, we invert the current axis. So, what do? We draw I to be positive and V to be negative, and in the fourth quadrant, earlier what was this? Let me draw it like this. So, earlier we have seen it will be somewhat like this, V and I. Now, if we invert I axis, this fourth quadrant will look like this, right. So, this is the fourth quadrant which is of operational importance. Others are good to know, but you are not going to get anything out of it. Okay? That is why this fourth quadrant, and we have inverted it. So, basically this is, we can say, I G. Okay? So, I G is the generated current under the applied voltage. So, I G is basically minus of I, and I G is minus of I. This I is from this plot. Okay. So, ultimately this particular plot we are boiling down to for photovoltaic effect. Now, let us look at this curve a little more closely, because that is what is important. Okay. So, let me try to draw this curve more clearly. So, usually the curve takes the shape, it is more or less flat and then comes down and then drops sharply. So, this is typically the shape of the IV curve. Okay. So, earlier we were doing just schematic diagram, now we are trying to make little more realistic what we get. Okay. Now, the point where it cuts the I axis, we call it ISC or short circuit current. SC stands for short circuit current, because short circuit means the voltage is 0 and that gives you the maximum current. Okay. And on the other hand, where you cut the voltage axis, that is we called VOC, which is voltage at open circuit. Okay. Open circuit means current is 0 and what voltage you get. Now, you can think of this point where So, what we are interested in VI, right? VI, the operational voltage and current product will give us the power. So, where it gets maximized? It gets maximized here, right, at the edge of the curve. So, this is called PM, or we often call it MPP, which is maximum power point. Okay. Maximum power point, and corresponding to that you can draw or you can find what are the corresponding voltage and current. So, this is called Vm and this is called Im. Okay. So, let me quickly write them so that it is clear. So, ISC is your short circuit current, that means I at V equal to 0 case, and then VOC is your open circuit voltage, which is V at I equal to 0 case. Okay. And this PM or MPP, that is the maximum obtainable power. Right. And Im and Vm are current and voltage corresponding to this PM point. Okay. So, you can see that ISC is the maximum current you can obtain, but for maximizing the power you can go only up to Im. Similarly, VOC is the maximum voltage you can go up, but that is useless because current will be 0. So, for maximizing the power, what you require to restrict yourself to Vm. So, if you operate it at Vm, then you will get the maximum power with a current Im. That is the same plot or same idea you can plot it in this PV curve. P means power, V means voltage. So, if we see that, it will be somewhat like so. This will be the maximum power point. So, when the voltage starts from 0, at 0 you have power also will be 0 and it increases as you go up, and then it decreases sharply near the VOC. Okay. So, we want what we want maximum power, and for that you have to adjust this voltage continuously to do the maximum maximize the power. So, that is called to adjust voltage or bias to track PM point with different operating condition is called maximum power point tracking, okay, or MPPT. Okay. So, you will hear this term if you go into the photovoltaics like jargon, you will find this term very often, MPPT. MPPT is maximum power point tracking, which is a must for getting the maximum obtainable power from a photovoltaic panel. Okay. So, some quick notes. Note that this ISC is nothing but IL. If you look back couple of here, IL is the current value when V equal to 0. Now, we have inverted it in the positive direction. So, ISC, the short circuit current, is nothing but the minus of light generated current, okay. And VOC is KT over Q ln IL by I naught plus 1. This you can just get by using that IV characteristic curve, okay, and then converting it to natural log from exponential. Okay. So, these two terms ISC and VOC, they are very much properties of that particular panel. Okay. The material properties are inside all these IL and I naught. Okay. Now, you can see, if you look at this particular diagram, you can see that the area under the curve of the IV curve is greater than what you get under the PM point. Okay. So, this is another note, that area under IV curve is greater than the rectangle corresponding to the MPP point or maximum power point. Okay. So, this difference in area is obtained through fill factor. Okay. Basically, the PM rectangle, how much of that is filling the IV curve. So, this fill factor, which is called FF, is the ratio of maximum power to that of the ideal power if both I and V are maximized individually, right, and that means your fill factor is VMIM, which is the area under that rectangle, and divided by VOC into ISC, and you can see it is often less than 1. The closer it is to the 1, the value of unity, the better performance we would say. Okay. So, closer FF to unity, better the performance. Okay. So, that is one quantity which talks about the performance metric, you can say, of the photovoltaic material or panel, and often you will hear this term efficiency. Efficiency is very simple, it is what power you are getting and by tracking the maximum power point, and power that is put in the material, that means solar power that is coming on the panel. Okay. So, this is available irradiance and this is the maximum power obtainable for the solar cell under the particular irradiance. Okay. So, that is the and typical efficiency values range from 5 to 15%. So, most of the panels that you will get can only convert about 10% of the available solar radiation into electricity. It is pretty poor. So, current focus in research is how to increase this efficiency to a larger value. And of course, there are materials, special material, and what we called triple junction solar cells. Okay. They can go up to 40%, which is a large number, but they are super costly. So, only when your efficiency is of prime concern you would use those kind of materials. Now, we will quickly look at the effect on this IV curve by the typical operating parameters. One operating parameters is the irradiance. So, irradiance effect. So, a cloudy day will have a less irradiance and you would expect that it will generate less power, right, and a sunny bright day will produce large or more power, right. So, how that effect is seen in the IV curve. Okay. So, if this is a particular IV curve and then if you go up in irradiance, the whole curve shifts. This is for a given irradiance. Now, if you go up in irradiance, okay, and if you go down in irradiance, okay. So, basically this direction we are going up. So, you can see that these maximum power points they are going up as well with the irradiance. Okay. And one more observation you can see, the irradiance, this current it is getting affected or the ISC getting affected more strongly than the voltage. Okay. So, ISC is affected more than the VOC, okay, by the irradiance change, but this PM increases with irradiance. Okay. That is the intuitive thing you can say. And another not so intuitive effect of temperature. Okay. Usually at lower temperature the photovoltaic efficiency or photovoltaic generation is much more than for the higher temperature. Okay. So, with temperature power output decreases. Okay. With temperature increase power output decreases. So, how does it affect the IV curve? Okay. So, now when temperature increases, the current decrease but voltage increases. Okay. So, you can see that here the maximum power point was here, but for increased temperature maximum power point drops slightly. Similarly, with drop in temperature, current will increase and voltage will decrease. Okay. So, that is how it is not overall shifting. What is happening here? The current is increasing, okay, with temperature increase. Temperature increase is happening in this direction, okay, and voltage VOC is decreasing. So, VOC is decreasing with temperature increase, and here ISC is increasing, and that is how the power is ultimately decreasing with increase in temperature. And you note here, unlike the effect of irradiation, here you have more. So, let me write, this is the effect on VOC and this is the effect on ISC. So, observation is VOC is more affected by temperature than ISC. Okay. So, typically temperature close to the room temperature 25 degree centigrade or even less than that is always better. So, if we are increasing the irradiation by some concentrator or something, then the temperature also goes up, and that actually reduces the efficiency of the solar cell. So, what we do? We put some cooling arrangement as well to effectively take into account this temperature effect. Okay. So, here I will stop for this class and as well as for the course, and here in this course I have tried to give you the elements. The title is elements of solar energy conversion. So, I have given you the elements. It is not like the complete description I have provided, and it is not possible to provide. If you look into a particular technology, it will take a complete course to go details of that. So, what I have done, I have introduced to all the different technologies of solar energy conversion and the fundamentals that are behind those technologies. Okay. So, I hope that from here on, if you go into solar energy conversion field, you will be able to take up from here and utilize the background to build up your knowledge on each and every technology. Thank you very much for your attention and for participating in this course. Good wishes. Thank you. Bye.